This diagram maps out the 30-agent framework. We're at the top of the Tools and Orchestration tier, moving into Node 9, Workflows. Previously, the chain of agents orchestrator optimized for inference speed, passing data in milliseconds. This focus on speed introduces a flaw. If a server crashes mid-process, an LLM suffers from complete context amnesia. The task memory vanishes. Real enterprise business processes rarely happen in milliseconds. They rely on external dependencies and multi-day wait times for management approvals. These workflows fail when an agent lacks the architectural capacity to pause and wait. Robust systems solve this by severing the reasoning engine from the execution layer. The LLM remains the brain, bolted to a durable execution engine that reports every step. Integrating AI into a corporate org chart requires engineering for patience, allowing the agent to survive unexpected interruptions without losing its place. Agent number 9. The Agentic Workflow System wraps the non-deterministic reasoning of an LLM inside a strict deterministic state machine. This architecture balances automation speed with risk governance. High-stakes transitions route to a human-in-the-loop gate, preventing costly LLM errors. A false rejection destroys trust. A false approval invites fraud. The system routes routine requests through the fast lane, holding risky ones for human review. Operating underneath this routing logic is an immutable audit trail. The system natively logs the exact condition that triggered the route and the human who cleared the gate. Agent number 9 serves as a governance protocol, providing a cryptographic receipt for every machine-made decision. We can observe this state machine managing a complex insurance claim. The operational lifecycle begins here, at the intake and validate block. An initial agent extracts text and enforces strict baseline requirements, checking policy status and cross-referencing fraud databases before the claim proceeds. Valid claims move to Node 2, the embedded agent node. An LLM calculates a fraud risk score. If the primary API fails, this node relies on a rule-based fallback mechanism to ensure the workflow degrades gracefully. This risk assessment is fed into Node 3, the guard conditions. These Boolean logic gates evaluate the risk confidence score to determine the next physical routing path. A low-risk claim with a confidence score of 0.91 satisfies the threshold. It bypasses human review entirely, flowing directly to process the payout. A claim with a score of 0.79 fails that threshold. The Boolean guard triggers, and the claim is rerouted to Node 4, the HITL escalation gate. This gate triggers a physical halt of the compute thread. The system freezes the agent's context, serializes the state to a database, and frees memory. The claim sits dormant until a human operator issues an approval. The system then deserializes the data, wakes the agent, and resumes the flow at the exact step where it stopped. Throughout this journey, Node 6, the audit trail, logs the acting agent, the action taken, and the specific reason for every transition. Confining specialized agents inside these transition boundaries transforms an opaque AI decision into a transparent, governed pipeline. These transitions are powered by specific execution mechanics in the underlying code. The workflow is defined as a declarative data dictionary. This transition table maps states directly to agent nodes, rather than using procedural if-else control flow. A simple Lambda function acts as the gatekeeper. It checks if the confidence variable meets the required threshold, providing the logic for routing to the human review state. At the escalation gate, a checkpoint saver mechanism takes over. The code invokes a yield command, returning the compute thread to the pool, while utilizing an update state command to write the current variables to a persistent database. The runtime uses a unique thread ID to match incoming human approvals back to the correct paused instance, allowing the system to deserialize the correct context days later. The log transition function executes at every jump, appending the origin state, destination state, and justification reason to a persistent database array. This ledger structure allows auditors to pull the logs and forensically replay the precise variables that led to any historical decision. This durable code harness provides the crucial security layer, physically wrapping non-deterministic AI reasoning within a completely predictable, stable execution environment. This architecture scales across multiple regulated industries. We see identical state machines managing loan origination, employee onboarding, and multi-tier procurement approvals. Any process requiring pauses, conditional branching, and audits requires a framework designed for persistence. Agent 9 remains trapped within the boundaries of the graph authored by the engineer. It executes the workflow, but cannot yet invent its own processes. The system does not alter its core structural graph on the fly to solve novel, unmapped problems. Despite this boundary, this workflow chassis provides the foundation for the specialized tiers ahead. Data analysis and code generation rely on this same write-test-loop shape to manage long-running tasks. To examine the code driving these checkpoints, review Chapter 7 of 30 Agents Every AI Engineer Must Build by Imran Ahmad and access the full curriculum at neuralsca. Autonomous enterprise AI depends on an engineer's mastery of how an agent waits, remembers, and defers to human judgment.